Uh, Testing. Can you hear me?
Yes, Rata.
Okay. So, Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to all of you. So, this is week 4. Okay. So, week 4. Just to remind you that we will have the first test. Okay, the first test on week 6. Okay, week 6. So, all the information about the test 1 will be maybe next week I will inform to you. Okay, so just to remind, early reminder to you. So the first test will be online on week 6. Okay, so without further ado, I think we continue with the full wave rectifiers, where as you may recall that from our previous class, so there are two circuits, or sometimes we also call as a topologies. Okay, we have what we call a full bridge, and also the second one is what we call a center tap. Okay, the center tap we are using a transformer. Okay, so meaning that there is a isolation between the source and also the load. Okay, so that one is actually what we have learned is actually for R load only. So the linear load, meaning that all the analysis calculation is actually very straightforward. Okay, but this time, so since we already know that actually the output for the full bridge and also the center tap, okay, center tap rectifier is actually same. Both are actually full wave rectifiers. So after this, we only concentrate using a full bridge, okay, for our analysis. Okay, the only difference between center tap the rating. Okay, the rating of the diodes. For the center tap, the rating of the diode is twice from the voltage source. Okay, that is the only difference. Okay, the other, for example, the output current, output voltage, the waveform is actually all similar. Okay. Okay, so let's go on this one, full bridge, where the load right now is a RL load or inductive load. Okay, so as you can see here, the output shown here is the voltage, which is a full rectifications. Okay, and the current is non-linear current as usual because we have inductive load here. Okay, but the current is actually in continuous mode. Okay, continuous. Okay, so and as you can see, there are no extinction angle. If you recall back for the half-wave rectifiers, we have extinction angle. Okay, that one is because of the energy inside of the inductor need to be discharged, right? And then it force the diode to turn on. Okay, but for the full wave, okay, there are no extinction angle. Why? Because as you can see here, when for the positive cycle, this part, okay, we know that D1 and D2 will turn on, okay? D1 and D2 will turn on. So the current will flow and then charge the inductor and then go back to the source through D2, okay? And then when at the negative cycle after pi, so D3 and D4 will automatically conduct because of the forward bias. So right now, this one is negative, this one is positive. Okay, so as you can see, since right now, the energy inside of the inductor need to be discharged. Okay, but since D3 and D4 is already on, so that's why it will continue to charge again. Okay, so meaning that there is no beta. There is no beta. If okay, so this you can see the current is charging here. Okay, and then at the some part it will start to discharge. Okay, it will start to discharge, and then when for the negative cycle, D3 and D4 will turn on. So meaning that it provide the route for this energy of the inductor to discharge and then also charge again. Okay, so that's why we have this continuous current waveform here. Okay, so unlike the half wave rectifiers where we have only a single diode, okay, so when positive cycle, the diode is turned on, okay, the current will flow and then it will charge this inductor. Okay, but when negative cycle, the diode is turned off, okay, and but this inductor need to be discharged, okay, So that's why it will turn on, force the diode to turn on. So that's why we have the output voltage like this, okay. We have this angle, what we call beta angle, okay, extinction angle. But for the full wave rectifiers, okay, so we provide D3 and D4 provide the route, okay, for the energy from the inductor to be discharged and then again charged again. Okay, so that's why we don't have an extinction angle here. Okay. And then this is actually the diode currents, ID1 and ID2, and also ID3 and ID4. And you have the voltage source is a sinusoidal, and the current is also a sinusoidal but distorted. Okay, so this waveform, even though it is a sinusoidal, but we call this current waveform as a distorted current. Okay, so meaning that your power factors will be very low. Okay, but this one is much better as compared to the half wave. So even though it's distorted, but still in terms of the power quality, okay, and then the power factor, this is still considered better compared to the half wave rectifiers with RL load. Okay, so the keyword here is actually a distorted. Okay, so this type of waveform selain daripada from the sinusoidal, so if the shape is actually not equal to the sinusoidal, so we call this as the distorted waveform. Okay, for power system. Okay, please mention that this is for power system. Okay, and this voltage average, then I think we can just use V2 Vm over pi, right? So this is your V output average. But the current right now is actually non-linear current. And it is very difficult to actually obtain what is the equation for the current. Okay, but since this is a continuous current, so we can use what we call the Fourier series. Okay, so the Fourier series to obtain, at least to obtain the I out RMS. Okay, to obtain this one. We can obtain this by using the Fourier series of this nonlinear current waveform. Okay, so I think you have already take the signal and system, right? Where you have been exposed to the Fourier series. Okay, so masa tu you ambil, you tak tahu pun what is the application of the Fourier series, right? Memang tak faham lah what is the purpose of studying this Fourier series. Okay, but actually the Fourier series is very useful in the power electronics. Okay, so because the Fourier series is actually, it studies the waveform, but not in the time domain, but in the frequency domain. Okay, so for this waveform, for the output voltage of this waveform, a cyclic rectified waveform, it says that Fourier said that it has two components, which is we call V out, which is the D component, which is this one is actually referring to the V out average, okay, which is you can calculate by using 2 Vm over pi. Okay, and plus with a component that we call harmonics component. Okay, so apa harmonics? Have you been exposed to harmonics? Have you heard about harmonics? Tak pernah dengar? Never heard? Okay. Okay. Just to maybe to make you understand about the power quality, okay? In the power system, lah, our power distribution and in electrical power, so we have two type of system, which is AC system. We have a DC system. Okay, so from this AC system, power quality, they have their target power quality, and for DC system also they have a power quality measurement. Okay, to determine whether the system has a very good power quality or not. For the AC system, the power quality is said that the voltage and current. So this is your voltage and then this is your current, both must be sinusoidal. Okay, must be sinusoidal and must be in phase. Okay, that is the objective inside the power system. If your voltage or current is not sinusoidal, for example, we have like this, the current. Okay, for example, like this, the previous one, like this waveform. Okay, which is not sinusoidal. So we call this current is distorted current, meaning that it has harmonics. Okay, it has some harmonics. So harmonics inside power system is very dangerous and we want to eliminate these harmonics. Okay, so meaning that if your current waveform has current that differ from sinusoidal, so we call this current have a, okay, that is for the AC system. Okay, same with the voltage lah. So if your voltage waveform is distorted, so we call that voltage has some harmonics component. Okay, for the DC system, for the power quality, so for the DC system, what is the target for the power quality? We should have a clean DC voltage and also a clean DC current. Okay, so since this is actually there is no frequency, so there is no what I call in phase or out phase. Okay, so for the DC system, you need to ensure that the voltage and current waveform is clean without any distortion. Okay, so if your voltage like this, you have some maybe ripple, okay, macam ombak. So this one we call this voltage has some harmonics. Okay, this current for example also have some this. Okay, so you say that this voltage and current has some harmonics. Like this also, if you have a voltage like this waveform, okay, which is the full wave rectifiers, so we also say that this voltage has harmonics. This is actually a DC because we call this a DC voltage because we see that there is no negative cyclic waveform here, right? All positive. So meaning that it has some DC component here. So same like this waveform, the output voltage of this rectified full wave. So this we call rectified DC voltage, but with a harmonics. Okay, so that's why we have a DC component here, which is represent the average voltage, where you can calculate using 2Vm over pi, and plus with a harmonics. Okay, and as you can see, this harmonics, okay, we actually refer the harmonics in the numbers, even numbers. okay, starting from 2, 4, 6, 8, and 10. Okay, and then this is your Vn. So Vn meaning that this is a variable depending on the numbers of the harmonics. And this one, as you can see, for the whole, this one, Vn cos n omega t, it looks like this is actually a sinusoidal waveform. Okay, so meaning that this waveform is consists of a DC component plus some sinusoidal waveform with a magnitude that you can calculate this magnitude of Vn by using this formula. Okay, cos and the frequency is n omega, which is you need to multiply with the numbers. Okay, so we have a variation of frequency and also the variation of the magnitude. Okay, so I hope you understand about the Fourier series. Okay, for the DC system. So it has the DC component plus some harmonics that we call this one is actually even harmonics because the number is even. So we call this one as a even harmonics. Okay. For the AC system, for example, if you have like this harmonics, so actually for the AC system, the harmonic start from 1, 3, 5, 7. So all is actually odd numbers. So that's why for the AC system, we call odd harmonics. So all in the AC system, only harmonics that exist is actually an odd numbers. While for the DC system, the harmonics numbers that appear is actually in even numbers. Okay, and then the voltage value is you can calculate by using this equation. 2 Vm over pi, and then 1 over n minus 1 minus 1 over n plus 1. Okay, clear on that? Okay, and then so from there, you can compute the current. So the current output average, this one is your I out average. Okay, so by using V out average, okay, which is this one 2 Vm over pi. So you just multiply over R, so you will obtain your I out average. Okay, and this In is referring to the current harmonics. So this N is actually starting from 2, 4, 6, 8, and so on. Okay, so how to calculate the current here? So you need to use this formula, Vn. What is your Vn? So Vn is this formula, okay, over Zn. And this Zn you can is actually only a magnitude, okay, magnitude. So you can use this one, R square plus n omega L square to get your impedance. Okay, and this value of impedance is actually not fixed. Okay, it depends on n. So Z2 is not equal to Z3. Sorry, Z4. Okay, because this n. The R is fixed, but the value of the XL is changing because we know that the reactance is value is depends on the frequency. This is your frequency n omega. Okay, because we know n omega is actually n multiplied with 2 pi f. So your XL will be changed, okay, according to the numbers of your harmonics. Okay, so actually as n is increased, for example, okay, for example, harmonic number 6, okay, 8, and so on. So when actually this Vn will decrease, okay, based on this formula. Based on this formula, so usually Vn will decrease when n is increased. Okay, while the impedance will actually increase. So when this Vn Zn is decreased and Zn is increased. So the value of the current I2 is larger than I4, and I4 is usually larger than I6 and I8. Usually I start from I8. That is what this two sentence to deliver. In calculation, we also maybe I2 or I6 only. It depends on the question. I8 and use almost zero. Okay, okay. So that's why sometimes for calculate the IMS. So this is actually the equation, okay, to calculate the I out RMS. Okay. So this one you can refer to the Daniel W. Hart chapter 1. Okay, in the chapter 1 in the textbook they have do some refresh, okay, on the how to mass, how to calculate the average for a certain type of waveform. Okay. So for this syllabus, we only show you that for this kind of waveform, which is a nonlinear waveform, we use this to average and IN, and from that can obtain the I out RMS. So the I out RMS is by using this equation, square root I out average square plus all the summation of the harmonics current RMS. Okay. So actually, usually if I use I4, so I can write down my equation to get the I out is I out as I harmonics number 2 square. So this must be RMS, okay? This must be RMS plus I4. Only like that, okay? Plus maybe I6. Okay, so how to get this I2 RMS and so on? So actually these values is actually peak values. Okay, peak value. So to get IN RMS, okay, what you need to do is IN over square root 2. Okay, so when after you have obtained the I or RMS, then from there you can calculate the total output power, okay, by using this formula. I RMS square multiplied with R. Okay. Okay. So let's look what happened when your omega. So right now our load is an inductive load. What happened when your XL is much larger compared to resistor, or we call omega L is much larger compared to the resistor? What happened? So next slide. So if the inductor is very large, okay, what you can see is actually the current. The voltage output is the same, okay, as a full wave rectified voltage. But the current right now is actually a pure DC current, okay, a pure DC current. So this is the output current when your L is much larger compared to the circuit. Okay. So if this condition is given, then your calculation has been made very simple. So since this is a DC current, okay, so your I out you can just use this equation, this I out average, out of R, which is 2Vm over pi multiplied with R. And since this is a DC current, so meaning that your IRMS is actually equals to I out average. Okay, so this is actually your I out average. Okay, so for DC current, pure DC current, without any harmonics or ripple, so your IRMS is equals to I average. Okay, why this happen? Because this one, this formula. Okay, we know that Zn is R square plus N omega L square. Okay, so if this part is much larger compared to the rest, so Z value of the Z is almost very high. So for example, it's very high. So if this Z is very high, and then you use this formula V over N, anything that is actually divided by a very high value, usually the current value will be almost zero. Okay, so meaning that I2 will almost zero, I4 will also zero, and I6 is also zero. Okay, so that's why the current is only a component only. Harmonics current is almost zero. Okay, this is this component is very large, so meaning that your is very high. If you are using this formula, anything that actually higher than divided by a high numbers below here, so it will become very small. Okay, so that's why we come out with this uh, uh, formula here. Okay, and the current input, as you can see, square wave. Okay, so positive, and then at the negative part is flip. Okay, this part is flipped to negative part back, and so on. So in terms of analysis, question that if you are been given condition, so the question will be very simple. Okay, so that is the case when your ohm L is much larger compared to the resistor. So issues related to the supply currents. So as I mentioned before, is actually the power quality. So the non-sinusoidal, so it will if some for example the power factors and harmonics content of the waveform voltage or current, we are using HD or what distortion. Okay, this one is actually in percent. Okay, usually for the current should be for the
Doctor.
the current should, okay. So the total harmonic distortion for the current is less than 5%, should be less than 5%. Okay. And how to actually, for example, to at the input side, we put a filters. Okay, a power filters. This one will be will be covered, okay, in your syllabus. Actually, the powertronics area is very big, okay. So we only cover for this syllabus, we only cover only the fundamental part only.
Doctor.
Oh,
low.
okay. Okay, sorry for that. I don't know. Okay. The line is
Doctor,
not
I have a
it's
question.
not clear, right? Okay. Okay, Afif, go on. Oh, okay,
Yeah,
Musab, you have any question? Okay. Okay.
yeah. I have a question with the previous slide, Doctor.
Okay, previous slide. Okay. This one?
Wait, yeah, this one for the yeah, like for the large voltages, Doctor. Won't
Yeah.
the harmonic the like the larger harmonics won't they have an effect
Larger
like in this
harmonics,
case?
what you mean?
Like I mean when the number is for the eighth harmonic or like the 10th harmonic.
Okay, okay.
Yeah,
So
yeah.
actually the harmonics, okay, harmonics, the number of harmonics for this, for example, this DC waveform, okay, this DC waveform, this DC waveform. So for this is your average, and this is your harmonics, which is the numbers starting from 2, 4, 6, 8 until infinity. Okay. But we usually didn't consider much. Okay, we only concentrate maybe harmonic number two, 4, or maybe 6 only, because actually if you plot the harmonics, okay, this one is V and this one is the harmonics numbers. Okay, this one is your VO. Okay, this one is your V6. This one is your V8. This one is your V10. This one is your V12. So actually it keep decreasing. Okay. If the number, okay, so higher numbers, so your harmonics will be very, very actually small. Okay. So that's why in the calculation, we on same with the current. Okay. For the current, you have the current average I out. Okay. And then you have I6, sorry, I2, okay, sorry, this one I2. So, and then I6, I8. So very, very small. It become very, very small. Okay. When N is increased, so actually the Vn will reduce. Okay. Same here. N is increased, so the current In will actually reduce. The magnitude will reduce. Okay. So that's why we only concentrate by using maybe I0, I2, and I4 or I6 only. Because this one is actually meaningless. Okay, if you want to calculate this and then compute in your to get your current, for example, I out RMS. Okay, which is you can get from here I out average plus I6 plus sorry, I2, I4. This one must be RMS. Okay, RMS square plus I8 RMS square plus and so on. So usually, for example, this one, we only concentrate until maybe 2 or 3 only. I2, I4, I6 only. Okay, because I8, I10 is already very, very small, and then the values is actually don't have any effect on the total current I out RMS. Okay, I hope I answer your question.
Okay, Doctor. Yeah,
Okay.
that's correct. Thank you.
Yang lain macam mana? Understand? This harmonic is very important, okay? Because we will deal with the harmonic in our chapter inverters.
So it doesn't matter if like the voltage is big or something. For like the further harmonics, they're gonna be close to zero.
Very, very small. Yeah, almost zero. Yeah, almost zero.
Okay, doctor.
So, okay, almost zero. Okay, I think, okay, we go for example 3. So, given a bridge rectifier has a voltage source, Vm given 100 volt at 50 Hertz and RL load with R 100 ohms and the inductor is 10 millihenry. So, determine the average current in the load. Okay, determine the average current in the load. So for this case, determine the average current. So I out average is V out average over R. Okay, so 2 Vm over pi over multiply with R. So 2 multiply with 100 volts over pi 100. So this one cancel out. So you should get around 2 over pi amperes. Okay. Okay, the second one, so determine the two higher order. Determine the first two higher order harmonics of the load current. So meaning that you need to calculate I2 and I4 only. Okay, the first two. The first two higher order, because we know that the current this one is I0. This one is not considered as harmonics. This one is your average DC component. And starting from this one, I2, okay, I4, I6. But this one, you only consider the first two higher order harmonics, okay, which is number 2 and I4. I6 is the third harmonic, so we didn't consider that because the question, the first two higher order harmonics. Okay, so what you need to do is to calculate your I2, which is V2 over Z2. And for I4 is V4 over Z4. Okay, let me look first whether I have a previous solution for this because it has it's a very time consuming. Okay, hold on. Okay. Okay, I'm sharing with you right now the solution. But this one I will maybe I can share with you now. Okay, so I have shared with you in the our WhatsApp group. Okay. Sorry. Okay. Okay, so the first one is I out average, which is 0.637 amperes. Okay, and the number 2 is the harmonics in the DC waveform, which is we know that the harmonics number is the even 2, 4, 6, and so on. But the question requires to only calculate the first two high order harmonics, which is number 2 and number 4. Okay, so and then by using this equation, what you need to do is to calculate the Vn first. Okay, so the Vn you can calculate by using this formula. Okay, I2, which is 2Vm over pi. Okay, multiply with this one. So from the calculation is you will get the voltage harmonics number 2 is 42.4 volt. Okay. And for the impedance that associate with the harmonics number 2, okay, so you can use your calculator directly by using the complex numbers, and from that you can use calculator convert into a rectangular form. Okay, for example like this. So please be careful that you may miss this n. Okay, so please make sure that you insert n here. So n omega L. So right now your n is 2. So 2 multiplied with 2 pi f. Your frequency is, this one is your frequency source. Okay, which is 50 Hertz. So you multiply this one, you will obtain the value of your impedance 2 is 100 plus J 6.28 ohm. Okay. So, but we only take the magnitude only. Okay. So, meaning that your your I2 is V2 over Z2, which is 42.4 volt over 100.2 ohm. Okay, so you will obtain this, which is 0.4235, 0.423. And for the I4, you get Z4 over Z4. Okay, so as you can see right now, the V4 is I use this one, so okay, 2 multiplied by 100 over pi, 1 over 3 minus 1 over 5, you will see that the value is very, very small compared to V2. So V2 is still large, 42.4, but the V4, as you can see, is almost very, very small, 8.5. Okay, and then it is, if you calculate V6, I think the V6 will be almost around 1 volt or maybe 0 point something. Okay, so that's why for the harmonic calculation, we only consider the first 2 or 3 harmonics only. Okay, so as been shown here, V4 is almost very small, 8.5 as compared to V2. Okay, and the impedance, okay, is 100.8. Okay, and then by using that formula, I4, you can calculate V4 over Z4 is almost 0. Okay, 0.084 as you can see here. It's almost 0. Okay, so I think for the harmonics current number 6 is, I think, almost also 0.001, I think. Okay, so we have finished calculate. So this is the answer. So I2 is 0.423 amperes, while the I4 is 0.084. Okay. Next is to calculate the power absorbed by the load. So to calculate the power absorbed by the load, you use this formula, which is I out RMS, but you need to calculate the I out RMS. You can use this formula, so I out square plus all the harmonics content, but we only consider two harmonics only. Okay, so harmonics number 2 and harmonics number 4. So please be mentioned that these values is the peak values. So you need to convert into RMS. Okay, so this is actually just divided by square root 2. Okay, so you will obtain the RMS values for I2 and also I4. Okay, and then finally you will obtain that this one is your I square. Okay, I square is 0.5, and then I can use this directly because the current is actually I square. Okay, so 0.5 multiplied with 100, so my answer is 50 watt. Okay, so I think that's all from me. You can see that in the WhatsApp where I have already shared with you. Okay, so this is almost in itulah pukul 2, pukul 3 ni. Student usually will be sleepy. Okay, but okay, I understand. Okay, so I think we stop here, and then
Doctor,
yeah.
can I know when is the date for test one?
The date for the test one,
Yeah.
if not mistaken, in the course information I have already state there.
Oh,
I think
already
30th
state.
of April.
Oh, after Raya, okay.
30th of April.
Oh, 30, is it?
Not. I think not. Not
Oh,
before
not before Raya.
Hari.
Okay. Okay.
Before Raya.
All right.
Before you celebrate the Raya, so we test you first.
Okay, Doctor.
30th of April on Saturday. Okay, Saturday I think night. Okay, night session around maybe 9 p.m. Because this one is actually synchronized with the part-time student in KL. Okay, so that's why we need to have that test in the weekend. Okay. Okay lah. So I just mentioned to you that you need to prepare for what you need to prepare for the test one. So since we have time here, so the first we will test you on the two chapters. The first one is the introductions, but we don't have yet discussed the question. Okay, so maybe after discussion, then I can maybe give you some tips on that. So the first one is the introduction. So all the on the device, okay, the characteristic of the device, and so on, and about the snubber circuit. That one is more towards on theoretical, maybe explanation and so on. Okay, and then the second question is a calculation, which is based on these chapters, but narrowed down to half wave with RL load. Okay, half wave rectifier with RL load or inductive load. Okay. So I think that's all that I can share right now. So on our next class, which is on next Tuesday, so we will still go on the single phase, but with the control. Okay, we are using the SER. So this one much will be I think will be very some part of it will be very hard for you if I try to continue today, okay, because we have two modes here. We have, it depends on the firing angle or depend on the delay angle. So we have the current to be in this continuous mode, and also it can be in continuous mode. It depends on the firing angle. So it has a lot of things to be discussed and analyzed. Okay, and then after that, we will go for the three-phase. I think next week also three-phase, but I think it's a very brief, okay, three-phase rectifier. So I will just go very brief, okay, and then because it will not be inside your test and also your final exam. Okay, I think that's all from me. Thank you very much for all your attention. So we meet again, inshallah, on next week. Okay, so thank you very much. Assalamualaikum
Thank you,
and
Doctor.
have a very good day.
Salam,
Okay.
doctor. Have a good
Doctor.
Assalamu alaikum.